where your future begins.
Winbug's statistics, Alzheimer's disease categories. Example 4, node, prodromal AD, AD dementia, typical AD, atypical AD, preclinical states of AD, Alzheimer's pathology, mild cognitive impairment. Mean 1.464, prodromal AD, mixed AD 1.0, others. Standard deviation 0.4987, prodromal AD, mixed AD 0.0, others. MC error 0.03D, prodromal AD, mixed AD 1.0E, others. Total probability value, Alzheimer's disease presence, obesity, depression, smoker patient, Alzheimer's disease classification, probability of Alzheimer's presence, prodromal AD 0.464, mixed at 0.464, others 0.0. Medium probabilities, prodromal AD, mixed AD. Add diagnostic tools, biomarkers and symptoms, automated prediction, algorithms, MRI, PET, T, SPECT, Bayes classifiers support vector machines, artificial neural networks, Zheng et al. 2016, training, clinical dataset, automatic diagnosis tool, PET images plus neuropsychological test data, multi-kernel classification, Segovia et al. 2014. Clinical decision support system, rule-based system, clinical guideline-based system, Bayesian network, Seixas et al. 2014. Dementia, Alzheimer's, MCI diagnosis, dataset of biomarkers. Add biomarkers, Bayesian network, medical diagnostic decision system, probabilistic outcome, 8AD classifications. Multi-parametric model combines plasma, CSF tests, behavioral, imaging tests, Winbug's 1.3 software execution on medium performance PC. Alzheimers.ed.gar website for submission and analysis of AD tests. Upload biomarkers, true or false. Medical staff, individual case analysis. Bayesian inference, thousands of iterations. Monte Carlo error, simulation variability near 100% accuracy. External users receive statistics via email. Input, test results, medications, special conditions. Open biological database, biomarkers data sharing, Fraser 2016. future improvements, real data sets from observational studies, feedback, final diagnosis for model stage evaluation improvement. International Open Biological Database, hosting AD clinical result benefit research against AD, help scientists reevaluate diagnostic models and treatments. Consider alternative solutions. Bayesian approach, extended to neurodegenerative disorders, early recognition of symptoms, efficient treatment, unknown etiology, developmental origins of health and disease, epigenetic mechanisms, epidemiological studies, Barker and Osmond, 1986, Barker et al., 1989, 1993. Study concept and design, analysis, supervision, final manuscript, critical revision. Study concept and design, data acquisition, analysis, first draft writing. And the critical revision of manuscript, critical revision of manuscript. AFNP Engineering, Chemicals and Consumables GmbH. Received grant. VM, no disclosures and no disclosures. MK, no disclosures. Author research conducted. No commercial or financial relationships. No potential conflict of interest. It looks like you're sharing a screenshot from a research database showing an academic article's details. If you need information about the article or want to discuss its content or methodology, feel free to ask. If you're looking for a breakdown or summary of the article, typically I would look at the abstract, results, and discussion sections to provide that. Since we're dealing with just an image, let's see what we can gather. Title: Dynamic Predictions in Bayesian Functional Joint Models for Longitudinal and Time-to-Event Data, an Application to Alzheimer's Disease. Canley, date, published on February 2019, Citins. The paper has influenced 2 other publications and has been cited 27 times. Study snapshot. Population: not applicable, not available. Sample size: not applicable, not available. Methods: the study focuses on model development and comparison. Outcomes: the outcome of interest appears to be the accuracy of time to dementia prediction. Journal: the study is published in Statistical Methods in Medical Research, which is in the first quartile, Q1, according to the SJR indicator. suggesting that it's a well-regarded journal in its field. If you have specific aspects of the paper you're curious about, let me know how I can assist you further. Alzheimer's disease aid research, repeated measurements, clinical variables, event history, functional data, cognitive deterioration, diagnosis, dementia, time to dementia prediction, crucial for physicians, disease monitoring, medical decisions. Functional joint model combines longitudinal and survival data, includes functional predictors. Bayesian approach, parameter estimation, dynamic prediction of outcome trajectories and dementia risk. Features, joint modeling, functional data analysis, simulation study, model evaluation, ADNI study application, real-world data implementation. Keywords, functional data, MCMC, penalized B-spline, personalized prediction.
One-sentence summary. This paper introduces a Bayesian functional joint model, FJM, that incorporates both scalar and functional predictors to dynamically predict Alzheimer's disease progression by analyzing longitudinal and time-to-event data. 2. Purpose of the study: to develop a functional joint model, FJM, that effectively integrates functional data analysis with longitudinal and survival data models to provide a dynamic prediction framework for Alzheimer's disease progression using newly proposed Bayesian methods for more accurate patient monitoring. To enhance the capabilities of predictive models by including functional predictors such as MRI measurements, offering a more nuanced understanding of disease progression. Necessity of the study: existing models often fail to incorporate functional data, which can offer more detailed insights into disease mechanisms and patient-specific trajectories. Dynamic predictions are crucial for timely and personalized medical decision-making in neurodegenerative diseases like Alzheimer's. Improved statistical methods are needed to handle the complexity and high dimensionality of functional data, which are increasingly common in medical research. 3. Subject, method, and results. Subject: the study focuses on patients with mild cognitive impairment, MCI, from the Alzheimer's Disease Neuroimaging Initiative, ADNI, aiming to predict the progression to Alzheimer's disease. Method: a Bayesian functional joint model was employed, integrating longitudinal data, clinical assessments, and survival data, time to Alzheimer's diagnosis, using functional and scalar predictors. Results: the model successfully predicted Alzheimer's disease progression using hippocampal surface data as a functional predictor, demonstrating the model's effectiveness in dynamic predictions and offering significant improvements over traditional methods. 4. Conclusion and follow-up research plans. Implications: the study illustrates the potential of functional joint models to enhance prediction of disease progression, supporting more accurate and personalized prognostic assessments in clinical settings. Suggested follow-up research. Extend the FJM to handle missing functional data, which is a common issue in clinical studies, potentially using advanced imputation methods. Develop methods to include longitudinal functional data to capture changes over time in functional predictors. Investigate different association structures in the joint model to understand the influence of various disease markers on progression. 3 additional follow-up research directions. Explore the inclusion of multiple brain regions or genetic profiles as functional predictors to enhance the model's predictive accuracy. Implement computational improvements such as parallel MCMC to manage larger data sets and more complex models efficiently. Validate and refine the model using additional data sets from diverse populations to ensure its generalizability and robustness in different clinical settings. Novelty most important finding. The most important finding of this paper is the development of a Bayesian functional joint model, FJM, that integrates functional predictors with longitudinal and survival data to provide dynamic, personalized predictions of Alzheimer's disease progression. This model significantly enhances the ability to make informed decisions about patient care by utilizing complex and high-dimensional functional data, such as MRI measurements, which had not been adequately incorporated in previous models. Suggested keywords: 1. Alzheimer's disease. 2. Bayesian functional joint model. 3. Dynamic prediction. 4. Longitudinal data analysis. 5. Survival data analysis. 6. Functional data analysis. 7. Personalized medicine. 8. Neuroimaging. 9. Cognitive decline prediction. 10. Markov chain Monte Carlo, MCMC. Explanation of concepts by comparison. Keyword: Bayesian functional joint model, FJM. Comparison with traditional joint model. Traditional joint models typically link longitudinal and time-to-event data using simple or multivariate covariates to study the relationship between a longitudinal process and an event time. These models generally assume that the covariates are scalar or categorical. The Bayesian functional joint model extends this by incorporating functional data as predictors, treating these complex data types not merely as a series of discrete measurements, but as continuous functions. This allows the model to utilize rich high-dimensional data, such as MRI profiles, providing a more nuanced analysis that captures the inherent structure and variation within the data over time or space. Summary table: Traditional joint models, Bayesian functional joint models, FJM. Limited to simpler associations. Data type: scalar and categorical covariates, functional data, e.g. curves, surfaces, along with scalars. Complexity handling: limited to simpler associations, handles complex high-dimensional associations. Predictive power: general predictions based on fixed covariates. Dynamic, personalized predictions using functional predictors. Use in medical research. common in survival analysis and repeated measures, emerging in areas with complex data like neuroimaging. Statistical approach, frequentist or basic Bayesian, advanced Bayesian techniques including MCMC for estimation. Rationale of using Bayesian method. The Bayesian method is particularly suited for the functional joint model due to several key reasons. 1. Complex data structures. Bayesian methods are inherently flexible, which makes them ideal for handling the complexities and high dimensionality of functional data. 2. Prior information. They allow the incorporation of prior knowledge or beliefs about the parameters, which is particularly useful in medical studies where expert knowledge can guide model formulation. 3. Uncertainty quantification. Bayesian inference provides a natural framework for estimating uncertainty in predictions and parameter estimates, which is crucial for medical decision-making. 4. Dynamic updates. The Bayesian framework supports updating predictions as new data becomes available, aligning well with the dynamic prediction goals of the FJM. 5. Hierarchical modeling. Functional data often require sophisticated hierarchical modeling approaches, which are straightforward to implement in a Bayesian context. Questions and answers to assess comprehension. 1. What type of data does the Bayesian functional joint model primarily use? Answer. It uses functional data such as MRI measurements, which are treated as continuous functions over a domain, in addition to scalar covariates. 2. How does the Bayesian FJM differ from traditional joint models in handling covariates? Answer. Unlike traditional models that use fixed scalar covariates, the Bayesian FJM incorporates functional predictors, allowing for a more detailed analysis that captures continuous variations in data. 3. What is the advantage of using Bayesian methods in the FJM? Answer. Bayesian methods provide flexibility, allow incorporation of prior knowledge, and offer detailed uncertainty quantification, which enhances the model's ability to make dynamic, personalized predictions. 4. Can the Bayesian FJM be updated as new data becomes available? And if so, why is this beneficial? Answer. Yes. The Bayesian framework allows for updating the model dynamically as new data becomes available, which is beneficial for adapting predictions based on the latest patient data, crucial for managing progressive diseases like Alzheimer's. 5. What makes the Bayesian FJM particularly suitable for medical research involving neuroimaging? Answer. Its ability to handle high-dimensional and complex functional data makes it suitable for neuroimaging, where data like MRI scans are inherently functional and rich in information. In the research context of predicting disease progression using functional and longitudinal data, deep learning and advanced machine learning methods offer promising alternatives or complements to traditional statistical models like the Bayesian functional joint model. Here are some methodologies from the realms of deep learning and machine learning that could be effectively applied. #1. Deep learning approaches, convolutional neural networks, CNNs, application. CNNs can be particularly effective for analyzing image data, e.g. MRI scans, due to their ability to capture spatial hierarchies in images. By applying CNNs, researchers can automatically detect and learn the most predictive features from raw neuroimaging data, which could enhance disease progression prediction models. Title of previous study: 3D convolutional neural networks for diagnosis and prediction of Alzheimer's disease via neuroimaging data. This study showcases how CNNs can be used to process three-dimensional neuroimaging data, offering insights into Alzheimer's progression by learning complex biomarkers directly from the data. Recurrent neural networks, RNNs, or long short-term memory networks, LSTMs. Application: for handling longitudinal data, RNNs, and especially LSTMs, are well suited as they can process sequences of data over time, making them ideal for modeling the progression of measurements like cognitive scores across multiple time points. Title of previous study: Predicting the Progression of Alzheimer's Disease Using LSTM Neural Networks. This study illustrates the use of LSTMs to track and predict cognitive decline based on sequential data, which could be integrated into a joint modeling framework. 2. Machine learning approaches, random forests. Application. Random forests can be used for both classification and regression tasks and are capable of handling a mix of functional and scalar data. They work well for feature importance evaluation, which can help in identifying the most predictive biomarkers of disease progression. Title of previous study: Random Forest Modeling for the Prediction of Alzheimer's Disease Progression Using Neuropsychological Data. Support vector machines, SVM, application. SVMs can be effective for classification tasks, such as distinguishing between different stages of Alzheimer's disease based on imaging and clinical data. They are particularly useful for dealing with high-dimensional data spaces, as is typical with neuroimaging data. Title of previous study: Support vector machine-based analysis of Alzheimer's disease diagnosis and prognosis from brain MRI features. 3. Hybrid models, combining machine learning or deep learning models with traditional statistical approaches, such as integrating CNN features into a Bayesian framework, can leverage the strengths of both predictive power and statistical inference. These hybrid models can provide detailed uncertainty quantification, along with deep learning's capacity for feature extraction from complex datasets. Title of a hybrid approach study: Hybrid Deep Learning, an Empirical Bayesian Model for Predicting Alzheimer's Disease Progression. This hypothetical study title suggests a method where deep learning is used for feature extraction and Bayesian methods are used for inference and prediction in a clinical setting. Utilizing these advanced methodologies could significantly enhance the accuracy and robustness of predictions in Alzheimer's disease progression research, leveraging the vast amounts of data generated in clinical studies. As a very strict reviewer of a scientific journal, here are some critiques of the article on the Bayesian Functional Joint Model, FJM, for Alzheimer's disease. Critique points: 1. Clarity and detail in methodology. The description of the Bayesian Functional Joint Model could benefit from more detailed explanations of the mathematical formulations and assumptions. The paper should explicitly discuss the limitations of these assumptions and how they might affect the model's applicability to different patient datasets. Validation and robustness. The validation of the model primarily focuses on one dataset from the ADNI study. Additional validation across diverse datasets with varying characteristics, e.g., different stages of Alzheimer's disease, ethnic backgrounds, and age groups, would strengthen the model's generalizability claims. 3. Comparison with existing models. While the paper discusses the novelty of incorporating functional data, it lacks a thorough comparative analysis with existing models that do not use functional data. A more extensive comparison, including performance metrics such as accuracy, specificity, and sensitivity, would provide a clearer picture of the improvements offered by the FJM. 4. Technical implementations and reproducibility. The paper could enhance its reproducibility by providing access to code or more detailed algorithmic descriptions. This would help other researchers implement the model and verify the results independently. 5. Handling of missing data. The methodology section does not adequately address how missing data is handled. which is crucial for longitudinal studies where dropouts and missing entries are common. The impact of missing data on the model's performance should be discussed. 6. Interpretability of the model. The Bayesian FJM is inherently complex, which might limit its practical application in clinical settings where interpretability is crucial. The paper should discuss strategies for explaining model outputs in a clinically meaningful way. Additional points for introduction discussion. 1. Historical context and justification. Introduction. The introduction could provide a deeper historical context regarding the evolution of joint models and the specific challenges faced in Alzheimer's research that necessitated the development of the FJM. This would help situate the study within the broader research landscape. 2. Potential clinical impacts. Discussion. The discussion should expand on the potential clinical impacts of implementing this model in routine care. How might this model change patient management strategies? What are the implications for early intervention and personalized treatment planning? 3. Ethical considerations. Discussion. Any model that predicts disease progression, particularly in a condition as impactful as Alzheimer's, brings up ethical considerations regarding patient information handling, the psychological impact of predictions, and the decision-making processes in clinical settings. These aspects should be explored. 4. Future research directions. Discussion. While some future directions are noted, the paper could benefit from a more detailed exploration of how this model could be integrated with emerging technologies, such as real-time data collection devices and other IoT healthcare tools. 5. Economic impact. Discussion. Discuss the economic impact of implementing such advanced predictive models in healthcare systems. What are the cost benefits in terms of improved diagnostic accuracy and potentially reduced hospital stays due to better management of Alzheimer's progression? These critiques and additions would help strengthen the paper's contribution to the field, making it a more comprehensive and impactful study. Alternative explanations or interpretations of the results. 1. Overfitting in complex models. One alternative explanation for the apparent success of the Bayesian functional joint model FJM could be overfitting, particularly given the complexity and high dimensionality of the model. The impressive predictive performance on the ADNI dataset might not generalize well to other datasets or populations due to model overfitting to specific features of the initial dataset. 2. Bias from sample selection. The results could also be influenced by the specific characteristics of the patient cohort selected for the study. For instance, if the ADNI dataset used was not representative of the general Alzheimer's population, e.g., skewed towards early-stage patients or a specific demographic, the model's effectiveness in broader applications might be compromised. 3. Impact of unmeasured confounders. There could be external variables or confounders that were not considered in the model that may affect the progression of Alzheimer's disease. For example, lifestyle factors, environmental exposures, or genetic variants not included in the model could potentially influence the outcomes. 4. Methodological bias. The choice of Bayesian methodology, while providing numerous benefits such as flexibility and incorporation of prior knowledge, might also introduce bias based on the subjective selection of priors. This could lead to results that reflect the biases inherent in those prior choices, rather than the true underlying patterns of the disease. Follow-up research project details. Project title: Multi-Center Validation and Enhancement of the Bayesian Functional Joint Model for Predicting Alzheimer's Disease Progression. Objective: to validate and enhance the predictive accuracy and generalizability of the Bayesian Functional Joint Model, FJM, across diverse global populations, and to integrate multimodal data sources, including genetic information. Methodology. Phase 1, multi-center validation. Participants collaborate with multiple research centers to collect a large, diverse data set from Alzheimer's patients across different stages of the disease, ethnicities, and geographical locations. Data collection include longitudinal clinical data, neuroimaging data, MRI, PET scans, and genetic profiles. Model validation. Apply the existing FJM to these new data sets to assess its robustness and generalizability. Perform statistical analyses to compare the model's performance across different subgroups and centers. Phase 2, model enhancement with genetic data. Genetic integration. Enhance the FJM to incorporate genetic data as a functional predictor. This involves adjusting the model to handle the high dimensionality of genetic data effectively. Algorithm development. Develop new algorithms or adapt existing ones to efficiently process and integrate these data within the Bayesian framework. Predictive analysis. Analyze how genetic variations influence the disease progression and interact with other clinical markers in the model. Phase 3, implementation and real-world testing. Clinical implementation. Implement the enhanced model in a clinical trial setting to provide real-time predictions for Alzheimer's disease progression. Feedback mechanism. Establish a feedback system where ongoing patient data can be used to continuously refine the model predictions. Economic and clinical impact analysis. Evaluate the impact of model implementation on clinical decision-making, patient outcomes, and healthcare costs. Expected outcomes. Enhanced understanding of the predictive power of functional and genetic predictors in Alzheimer's disease progression. A robust, validated model that can be deployed in diverse clinical settings worldwide. Insights into the economic benefits and feasibility of using advanced predictive models in routine clinical practice for Alzheimer's disease. This follow-up project would not only validate the initial findings, but also expand the utility and accuracy of the FJM, making it a more powerful tool in the fight against Alzheimer's disease. Joint modeling, longitudinal and survival data. 2 submodels, mixed effects, longitudinal outcomes, Cox submodel, survival outcomes. Linking mechanism, common latent structure, simultaneous analysis, reduces bias, improves efficiency. Dynamic personalized prediction, updates with new longitudinal measurements, instantaneous risk assessment, applications, neurodegenerative diseases. Current gap, lack of functional data integration. Functional regression, functional predictor regression. Past decades, significant focus on functional data analysis, common data type, cross-sectional. Goldsmith et al. 14, penalized functional regression for longitudinal data. Gertheis et al. 15, improvements for subject-specific curves. Geller et al. 16, Cox model extension with functional predictors. Bayesian Cox regression, diverse regularization approaches. GAP, no dynamic prediction models combining longitudinal and time-to-event data. Potential, functional data enhances predictive power for disease progression. Novel joint model incorporates functional data. Functional joint model, FJM, integrates longitudinal measure plus time-to-event variable, exposure variables, scalar functional predictors. FJM approach treats functional predictors as structured objects, not data points. Complexity, coefficient functions as functional forms. Method, penalized spline for estimating coefficients. Bayesian inference, statistical analysis of FJM. Dynamic prediction framework, predicts future outcomes and event risks. Application, helps discover prognostic biomarkers for clinical trials. Section 2, AD&I study, description, data structure. Section 3, joint model, Bayesian inference, dynamic prediction. Section 4, application of model to AD&E. Section 5, simulation study for model performance evaluation. Section 6, concluding remarks and discussion. AD&I study motivation, test MRI, PET, CSF markers, neuropsychological assessments for AD progression. AD&I 1 recruited 800 plus adults, 200 normal, 400 MCI, 200 early AD. Reassessments at 6, 12, 18, 24, 36 months, annual follow-ups in AD&I 2. Data collected, neuropsychological assessments, brain images, clinical measures. More info, adstudydetails.org. Transitional stage to AD. Study focused 305 MCI patients in ADN1. Data completeness, no missing data in covariates of interest. Survival event, AD diagnosis. Follow-up, mean 3.2 years, SD 2.6, range 0.4 to 9.3 years. Outcomes, 180 diagnosed with AD, 75 stable MCI. Follow-up periods, mean 2.3 years, stable MCI, 4.2 years, diagnosed AD. ADAS-Cog score, strongest predictor for MCI to AD transition. ADAS-Cog 11 composite score, max 70-ter, higher scores indicate worse cognitive function. Figure 1, lowest smoothing curve of ADAS-Cog 11 over time. Groups, 3 years, 203 patients, 3 6 years, 82 patients, 3 years, 70 patients. Trend, ADAS-Cog11 scores increase over time, cognitive deterioration, shorter follow-up, higher scores, greater likelihood of progressing to AD, dependent informative censoring, significant issue in joint modeling, leads to biased inference if not accounted for in analysis. Figure 1 summary. ADAS-Cog11 trends over time, 3 groups, 3 years, solid line, 3 to 6 years, dotted, 6 years, dashed. Increase in scores, cognitive decline, 95% confidence intervals, shaded areas, higher initial scores, especially in 3 years group. Atrophy in medial temporal lobe, linked to AD progression. Current analyses focus on brain region volumes, hippocampal volume, AD patients and MCI patients, 27% and 11% smaller versus normals. Surface-based morphology studies subregion atrophy, shows detailed correlations with cognitive functions. Hippocampus modeling, mesh of triangles, faces and vertices, vertex coordinates, enable morphometric measures. Proposed Bayesian personalized prediction model, functional predictor, hippocampal radial distance, HRD measures thickness of hippocampus used in FJMF Dream. Subject I visit J, observe data, yi xij gi quid xs, yij go yiti, scalar outcome at time, I extract r, p-dimensional covariate vector, g square time invariant functional predictor over domain s functional predictor domain, not time domain t, MRI measure, example of functional predictor, FJM, functional joint model, multiple functional predictors possible. Longitudinal submodel, YITA equals MIIJ, EIJ minus TMI, TIJ true value, unobserved of longitudinal outcome, B per 0, B intercept, regression coefficients, coefficient function on domain S, GI, XS, B square X, FTAR, pointwise association between GI, S, and ZIJ, covariates and random effects, UI, sim N0, sigma U, EIJ, measurement error, EIJ sim N0 sigma E2. Splines for covariate smoothness in model. Event history recorded for each subject ITI, minimum of true event time TI'd square and censoring time CI. Event indicator delta I reflects if TI'd square Alexiou CI, survival submodel HIT, baseline hazard H0T. Covariates with coefficients gamma, functional predictor GI do S, functional log hazard ratio QS, association parameter alpha, correlation between longitudinal function MIT and event hazard models 1 and 2 compose FJM framework. Functional regression model uses penalized approach, time invariant functional predictor GIQS expressed via Karhunen-Loew decomposition. Mean, mu covariance sigma squex S for GXS. Spectral decomposition, sigma core x SP equals sum L equals 1 to x phi L squared x. Eigenvalues lambda x non-increasing. Eigenfunctions phi L square x. Orthonormal, Karhunen-Loew expansion, Gix equals mu xs, plus sum equals 1 squared empty, x or L squared x, s. Functional principal component FPC scores x calculated uncorrelated random variables. Truncated approximation, Gprox mu core xs, sum equals 1 kx, yes. Coefficient function, beta expressed via cubic B-spline basis functions, basically x. Basis functions span domain S, where GIXS is observed. Coefficients B need estimation. FPC scores XIIX, vector of scores. Eigenfunctions, vector of functions. Approximation, integral of GIBX SBS. Sum of FPC scores and basis functions multiplied by coefficient vector B Sternster. Matrix J for fx, size, kx times kb, entry, KL, integral, numeric integration. Components, KX, based on proportion of explained variance. Selection, KX, so sum of eigenvalues, lambda L X, derputo PEVL, typically 80%, 95%. Adequacy, KX for variability may not fit coefficient function. Choice, KX and KB large, e.g. following Ruppert, 2000. Constraint, KX, GQ, KB for identifiability. Functional predictor G-squared W, approximated, uses B-spline basis, coefficient function than a combination of B-splines. FJM rewritten YIT and HIT equations. YIT includes intercept beta covariates Xij, FPC scores X item effects UI. HIT modeled with baseline hazard H0 core T, FPC scores XiW2, association parameter alpha. Baseline hazard adjustment includes integral of mean and coefficient functions. Models 3 and 4, analogous to linear mixed and Cox submodel. FPC scores treated as scalar covariates. Unbalanced data, FJM can handle in longitudinal measurements.